Welcome to the 10th lecture of graph theory. We will recall what we were doing in the last class. This was the theorem we were considering. If G is a 3 connected graph with greater than 4 vertices, then G has an edge E such that if you contract that edge, then G, the remaining graph is again 3 connected. Such an edge you can always find in a 3 connected graph of with number of vertices greater than 4. If the number of vertices is equal to 4, you cannot possibly do that, because if it is a K4, if you contract, you end up getting a K3. If you contract any edge, you end up getting a K3, and it is not 3 connected, it's only 2 connected. So this condition that the cardinality of the number of vertices is greater than 4 is important. So now we had already done half the proof, so we will go back to the main points of the proof, and then we quickly recall what were the main things. So the key ideas were that suppose this theorem is wrong. That means we have a 3 connected graph with more than 4 vertices in it, but every edge is such that if you contract it, you end up getting a graph whose connectivity is less than 3. That means with a 2 separator, vertex separator of cardinality 2. Suppose such a graph exists, so we will show a contradiction. So we say that it's not possible, because then it will give rise to a contradiction. So the idea was to observe that if each edge, say xy is an edge, if it is contracted and we get this vertex vxy, and then if it so happens that the resulting graph is not 3 connected, that means there exists a separator of cardinality 2 in it, then that separator should definitely contain vxy. We have already explained why this should be true in the last class, and then there should be one more vertex in it. So we considered such an edge, such a separator, and this separator correspond to the the vertex separator of cardinality 3 xyz in the original graph, right? So for every edge we have a corresponding separator, because when we contract that edge, we can get a partner for it, say here z, so that xy and z together will form a separator of cardinality 3, minimum separator in the original graph G. Now we will associate with each vertex xy a value. So we can always take the partner which will give you the best value according to this definition. The value was that we consider the cardinality. So if you remove this 3 vertices, this 3 separator xy and its partner, then consider the components that results from removing these 3 vertices, and then we look at the smallest cardinality, smallest sized component. The number of vertices is wise minimum component we will look, and the number of vertices in that component will be the value of this thing. Now we pick up in the next step, we pick up that edge xy such that xy and its partner set together has the minimum possible value among all such selections, right? So we will, the contradiction that we are going to show is, we will end up, in this case we will end up with another edge which will give you an even smaller value, which will be a contradiction. So this was the proof. You consider this x, y, recall this, there is an edge here and its partner set. Now let this be C be the component of smallest cardinality. This is the smallest component. Now a interesting property of the minimum separator or minimal separator, whichever, is this. you, for instance, you will, if you look at this vertex, you will have a connection to this component. The connection to this component, there will be a connection to this component that we have explained in the last class. Suppose that connection is not there, you could have, so for instance, if you had a so called minimum separator here, and then here is one vertex which is not connected to a component here. This is a component. So this is, there is no connection between this then this component. Then even by removing this much vertices, I mean removing all the vertices of the separator except this, we could have disconnected this portion from the remaining graph, right. Therefore, it's always true that every minimal separator, in particular minimum separator also, every vertex of the separator will be connected to connected by at least one edge to every component, like this. It will be like this. Yeah. It's not possible to have one of the vertices not having any edge to a component. So coming back to this picture, here this set also has a connection here, right. And then let this connection, at least one connection is required for us. So we will take this vertex, let this vertex be called V. So we take this edge set V, we will analyze the value that will come for set V, that will be given to set V. In other words, set V is an edge, so it should have a partner, let us call it W. This W can be from here or here or anywhere. So there are other components, maybe some here, 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 we don't know, wherever. W can be from anywhere, but it's a partner of set V. So the set VW, when you remove it from the graph, we will end up with several connected components. What would be the size of the smallest component? Will it be less than the cardinality of C? In which case we are already we have already found a contradiction, because we have assumed that among all the edges xy had the minimum value, and therefore the C is supposed to be the smallest. You cannot get any smaller component than C when you remove Z, V and W from the graph. So it essentially means that, so if you can somehow show that when I remove Z, V and W from the graph, a smaller component will result. So then we will get the required contradiction. So of course you can see that if I remove Z, V and W, this V is already disappearing from C. So there is a chance that we may get a smaller component. So if you want to, if it doesn't happen, what is the thing? Somehow this this C should eat up other vertices and become bigger, right. So somehow C should get more vertices attached to it and then become bigger. Otherwise already this is showing a tendency to become smaller than the C. So one thing we can be clear is this will not split into more than one component, right, because if it split into more than one component, see, of course, see, for is it possible that both the components will get some outside vertices and grow? The only way to get outside vertices is to attach to this x, and then of course this y will come along with that. X and y together will go to the same component, and then it may catch some outside vertices like this, right, and then grow. So only one component can get x and y. So therefore only one component from, if we split this C into several pieces, only one such piece can get more vertices from outside. So it's not possible for C to split into more than one component, one piece, because one of the piece at least will become smaller than the original C. So only because if it becomes more than one piece, only one among them can grow larger by taking this xy and more from outside, because the only way to take more vertices from outside is to connect to xy first and then get more vertices. So the thing is, it's not possible to connect to x, one component connect to x and gets more from outside, the other component connects to y and gets more from outside, because x and y, because there is an edge between them, they have to belong to the same piece, right. So that is if at all they are still there. So therefore so we can assume that C has to be together there. Now the only thing we have to worry is now V is removed from C. So definitely it has to get some vertex x or y attached to it, otherwise it's already going to be smaller than the original C. So it will get x and y attached to this, and now more vertices can be attached to this. But then if you look at the current picture, so you can see that, so we have our Z V and some W somewhere, and then here is this component which contains our old vertices of the C. It's possible that it have captured x and y and become bigger, that it has to, in fact something more also, right? And then some other component, one more component at least is there. Now where are the neighbors of V is the question. So the neighbors of V, if you remember, the V is from here, its neighbors can be somewhere here, or it has to be this x or y, right? Z is already we have taken in the separator. So all the neighbors of V has to be in this collection. So maybe here also x, y, and somewhere here. So we will not have any neighbor to any of this other components, this component or this component. So all the neighbors of V is only to one part, which essentially means that, so this is not a minimal separator at all. This is not a minimal separator. This is not a minimum separator. So this is a contradiction. We told that for every edge, when you contract, you will get a partner W. So that said, W is a minimum separator of the original graph. Now we are saying that this V is connected to all these things, and without V, then W itself will in fact separate these portions from this portion, because this is only connected to this portion, right? So that is the contradiction coming. So therefore we can conclude that every edge cannot be such that when you contract that edge, it becomes less than, connectivity becomes less than 3. So there should be at least one edge by contracting which we can retain the 3 connectivity. This is the essence of that theorem, right? The proof. So to conclude, that was a proof by contradiction. So essentially we assume that the theorem is not true. That means for every edge, when you contract, you can find another vertex, which I call as its partner, such that x, y, and that vertex Z, say partner, will become together a 3 separator of a vertex separator of cardinality 3 for this graph G, original graph G. And then we analyze the smallest component, and then, so let's say x, y be the edge which gives the smallest component, and then we showed that there will be another edge by contracting when we consider the corresponding 3 vertices, that will give you a smaller component, which will be a contradiction. This is the essential feature of that. Now how are we going to use this thing? So this is a main statement we want to prove finally using this. So if graph G is 3 connected, if and only if there exists a sequence G0, G1, Gn of graphs such that the following properties hold. So the first graph G0 is equal to K4, the smallest 3 connected graph K4, and Gn is our graph, the last graph is our graph. And also Gi plus 1 has an edge xy with d of x greater than or equal to d of y greater than or equal to 3, and Gi is equal to Gi plus 1. I mean Gi is obtained by contracting the edge xy from Gi plus 1. See, one side of this thing is very trivial. You give me any trivial in view of the thing that we have already proved, the result we have already proved. So you give me a 3 connected graph. Of course, every degree is greater than or equal to 3 there, because it's 3 connected graph. Now what you do, you can always find out that particular edge which is guaranteed to exist by our previous lemma, so which will allow, which is such that by if we contract that edge, the 3 connectivity is not lost. The resulting graph is again 3 connected. So this particular edge, if I contract, I will get a smaller graph, smaller by one vertex. And then I take the new graph, it's again 3 connected. As long as it is greater than, the cardinality is greater than 4, you can again find an edge such that if we contract that edge, still we can retain 3 connectivity. We can contract that edge and we will get a smaller graph, smaller by one vertex, and then we can find out, because it's again 3 connected, we can find another edge with the same property and keep going until we reach the situation that the number of vertices is 4. Number of vertices is 4, but the number of vertices 4 and it is 3 connected means it has to be K4, right. So therefore, given any 3 connected graph, we can get a sequence of graphs Gn equal to Gn minus 1, Gn minus 2 up to G0, which we call as K4, we call as G0, that is the K4, right. We will be able to reach. That is very obvious from that earlier lemma we proved. The other way, suppose somebody gave you a K4 and you start doing it, you pick up an edge xy such that both the degrees of dx and dy is greater than or equal to 3, and then you kind of do the opposite of contraction. That means if you get a graph such that if you contract, sorry, so not like that, if you start from K4, and if you can find out a graph from that such that this K4 can be obtained back by contracting an edge xy such that both of its degrees are 3, then you can say that this operation will lead you to a 3 connected graph. This is a straightforward statement, in fact. So if you want to rigorously prove that, so you take any graph K4, so you can say some Gi. So now currently we have a graph, let this be 3 connected, right. That means the minimum separator cardinality is 3, and then or more, 3 or more. So now we found out a graph Gi and Gi plus 1. It so happens that there is an edge in Gi, which is xy edge, such that the degree of x and degree of y both are greater than or equal to 3, at least 3 is there, and when you contract this edge we get this, right. Or in other words, Gi plus 1, when you contract this edge, xy edge, we end up getting Gi. In that case, I want to say that this is also 3 connected. Suppose this is not 3 connected, then we will get a minimum separator of cardinality 2. So there are 2 components on the sides. So this is the Gi plus 1. Now you can see that, is it possible to have both my x and y on one side of this thing? That means x and y doesn't belong to this, this is here, so or here. So what will happen? So if I contract this thing, we will replace it by Vxy. So Vxy, and this will, after contracting, what we get will be Gi, and then but then Gi is not supposed to be to have any separator of cardinality 2. So but then here you can see that this is going to remain as a vertex separator for Gi also. So it's not possible to have x and y both on one side, because if you contract that, we'll end up getting a separator of cardinality 2 for Gi also, right. So neither is this possible nor is this possible, right. So this, both the situations are not possible. So the only situation is maybe you can have at least one x here, x or y, one of them here or both of them here, something like that. So but then the key thing is, see, there should be something on this side, say, so y is here. So suppose there is something on this side and something on this thing. So suppose there is another vertex here other than y, so x I am putting here on this thing, suppose some v is here on this side. Then also the same situation, suppose if I contract, so you see these 2 vertices is enough, this Vxy and this other vertex is enough to separate V from this part, V from this part. So we will get end up getting a separator, minimum separator of cardinality 2 for GI also, which is not possible. So the only conclusion that we can make is that the situation is like this. So we have an x, we have some two separator here. So one of them is x, the other is y, and this y is the only thing here. Y is the only thing here in this side. And then, but we also know that d of y has to be greater than or equal to 3. Where are the degree 3 edges? 3 edges should go out of this thing. Where will it go? One can go here, the other can go here, but where will this go? So there are only two vertices here, there are nothing else here. So that leads to a contradiction to this assumption, and so it's not possible. This is not possible. So we conclude that. So we conclude that. So if we start from a GI and GI and find out a GI plus 1 and an edge xy in GI plus 1 with degrees dx and dy both greater than or equal to 3, such that GI plus 1 contract, when you contract the edge xy in GI plus 1, we end up getting GI. Then if GI is 3 connected, GI plus 1 also has to be 3 connected. So this is what you are told. So that's the other side of it. This is in fact easy to prove, and from the using elementary arguments, while the other thing, that means given a 3 connected graph, you can get a sequence of graphs reducing the number of vertices one by one and reaching K4 such that each member in the sequence is 3 connected is required that lemma which we proved. Alright, so that is the end of it. So this is the way 3 connected graphs are characterized. Now we will go back to the connectivity theorem, the main theorem which we mentioned in the first class, the connectivity, the Menger's theorem. That is what our next aim is. So let's see. We need some definitions here. So we need to convert the notions into a little different, because into a slightly different way, because we are going to prove the Menger's theorem in a slightly more general setting, following Reinhard Distel's book. So we consider the sets A, B subset of the vertex set. We call a path P. So that let's say the path is x0, x1 up to xk, which this is called an AB path if the first vertex of this path belongs to A, that means x0 belongs to A, and the only vertex from the path that belongs to A is x0. That means the path starts off from A and it will never come back to A. Similarly, the last vertex of the path belongs to B, and the only vertex of the path that belongs to B is the last vertex, namely xk. I mean, once it reaches B, it does not move further, right? This is the AB path. Another notion we want is AB separator. See, when you say AB path, before going further, let's look some interesting things about AB paths. So here, when I mention AB paths, this A and B, don't think that A and B has to be disjoint sets, or so for instance I can take this small graph. So this is a small graph. Here this can be A, this can be B, so this can be B, this can be B, this is A and this is B. Now an AB path can be like this, right, because it starts off from this thing and reaches here. Now it's also possible that so you can have this A is this and B can be this and also this. That means you can have a common vertex between A and B. A intersection B need not be phi. In that case, this vertex can be considered as an AB path. This vertex itself, the singleton a path which contains only one vertex. Similarly, it's possible that our B contains this and A contains this. Then this edge can be considered as an AB path. So, in other words, when I say AB path, I am not assuming that A intersection B not equal to phi or something. So, there can be common vertices in A and B. In that case, that single vertex, each vertex in the A intersection B is an AB path. AB path. Understood. Now, also it's possible to have direct edge from A to the set A to B. All such possibilities are allowed. For instance, yeah. So if for instance it is possible that A is a subset of B, right? A is a subset of B, in which case the vertices of A, each of them will define one AB path of just one, having one vertex each. So that's all the AB paths. So whenever we say AB paths, like in the Menger's theorem, we were interested in the number of internally vertex disjoint paths between two vertices A and B. Here we have converted the notion to just so that in that case there were two vertices X and Y. We were interested in the number of maximum number of internally vertex disjoint paths between X and Y in the graph. So how many are possible? So the only condition was it should be internally vertex disjoint. The only common vertex is X and Y. Here we have generalized it to some sets A, instead of one vertex we take A and this internally disjoint property is kept in some sense because we want disjoint AB paths, right? We don't want not internally disjoint, we say disjoint AB paths are required. Suppose disjoint AB paths are required. So we can always, like here we can ask here also, how many such AB paths can be obtained. Here, when I say AB path, they have to be disjoint. Here I only wanted internally vertex disjoint things. Here I want disjoint. That means one AB path, even the endpoint should not be shared. So in other words, how many such AB paths can be there? So definitely we cannot have more than minimum of cardinality of A comma B, right? So that is an upper bound for the number of possible disjoint AB paths. So this is the parameter we will be studying. So as I told, so minimum of cardinality of A comma B is an upper bound for the maximum number of AB paths, disjoint AB paths, right? So because each AB path will take away one vertex from A and one vertex from B. So when one of them finishes, then we won't get any more. Similarly, if you consider this quantity A intersection B, so each vertex in A intersection B will define an AB path. Therefore, this maximum number of AB paths has to be at least as much as this. So this is some trivial lower and upper bounds for the number of AB paths. So we will come back to the number of AB paths a little later. We will first look at another concept here. So here is another concept. Given A, B, like earlier, I am not assuming that A and B are disjoint or anything. So A and B, and then we say that a collection of vertices X is such that if it is such that every AB path in G contains a vertex in X, then we say that the this set X separates the sets A from B in G. So in other words, given A and B, we are looking for another subset X such that if I remove X from the graph, there won't be any more AB path in the graph, or every AB path should pass through this X. So then we say that x separates AB. So here again you can see that like earlier, because we don't have any condition that A and B has to be separate, so we can have A intersection B not equal to phi, right? In that case you can see this A intersection B has to be a subset of the x if x separates A from B, because any vertex in A intersection B remains in the graph, then there is an AB path, namely that trivial singleton vertex path, single vertex path, right? A to B we can reach. Similarly, if you can see that if A is this and B is this, there is an edge between them, so at least one of these vertices should belong to x, otherwise this path will remain, right? This is a one edge path. So right, so if for instance if A is a subset of B, then all the vertices of A are the only possible collection of AB paths. The vertices to separate A from B, we have to remove take x equal to A itself, otherwise we will not be able to separate, right? So essentially you can see that x, when you say x, the sets that separates A from B, I am interested in minimizing the cardinality, of x, right? I want to, given an A B, I will be interested in getting this parameter k of A comma B comma G, that is the minimum number of vertices in any set x, so that x separates A from B. K B is equal to cardinality of x, right, which minimizes the sets A and B. So the minimizes the set x, the cardinality of the x, which can separate A from B. So earlier, so of course these two parameters, the cardinality of the path, AB paths, maximum cardinality of the number of AB paths, and the minimum cardinality of a set of vertices, subset of vertices x, which can separate A from B. These two parameters somehow correspond to the two parameters we earlier discussed, namely given two vertices, the local connectivity was defined to be the maximum number of internally vertex disjoint paths, and also we told that the minimum number of vertices to separate x from y was another parameter. Our intention was to prove that these two are equal, right? Instead of proving this thing, we will prove this general statement that give me any two subsets A, B, then we will show that the maximum number of AB disjoint AB paths equal to the minimum x, cardinality of x, that separates A from B. So minimum cardinality of x that separates A from B. So more formally I can show you the A, B subset of A of G. So now here a graph and AB subset of E, then the minimum number of vertices separating A from B in G is equal to the maximum number of disjoint AB paths in G, right? This is what we want to prove. See, before before getting to the proof of this thing, let's look at some interesting features, like you can take a bipartite graph, right? So A, B, you can take a bipartite graph and then let this side of the bipartite graph itself be the set A and this be B. Now what are the if I ask for the maximum number of disjoint AB paths in this graph, what is that? So once you can say that if there are no singleton paths here too, because they are disjoint, right? There is no intersection here. So you have to start from here and reach here. You have to start from here and reach here. So the so you can take an edge, but then once you take an edge, you cannot come back, because you already touched B. So the only possible AB paths are the edges. Any edge is an AB path. You can start from here and you reach here. You start from here. Why you cannot take more than an edge? Because if you if you take an edge, already you are in B, and the AB paths doesn't allow you to go further once you reach B. So therefore, the only AB paths you can take are at the edges, but then they have to be disjoint, independent. So what are they? In fact, the maximum number, that is essentially the maximum matching, right? The maximum matching. So we can say this is the alpha dash of G, right? So this may come out as an interesting observation, that this maximum cardinality of the AB paths in this graph, in any bipartite graph, when I take A to be one side of the bipartite graph and B as other side, then it's indeed the maximum matching that we are talking about. Now again, for this bipartite graph case, when you take this A and B, and you can ask what will be the minimum cardinality of X, any separator of A and B, right? But according to the definition. Now you see the separator should be such that once you remove the vertex, suppose here is the separator. So once you remove the vertices of the separator, we will not get even one edge in this across. Why? Because even if one edge remains, then A is not separated from B, because there will be, this edge is an AB path, and then there will be an AB path, path from A to B. So all the edges should get removed when we remove the vertices of X from the graph G, if it is an AB separator. In other words, every edge should have at least one endpoint in this X, which means X is a vertex separator. X has to be a vertex separator if it is an AB separator here. In other words, the minimum cardinality of the X, the sets X that separates A from B, is essentially the cardinality of the minimum vertex cover, beta of G. So if we manage to prove Menger's theorem, that is the maximum number of AB paths, the disjoint AB paths is equal to the minimum possible cardinality of a set X that can separate A from B. It's equivalent to proving here, in this case at least, in this case, that alpha dash of G is equal to beta dash of G. In the bipartite case, when we take the A and B to be the two sides of the bipartite graph, right? So therefore, so it's so this generalization is not that bad. So it's able to capture some things which at one look we may not notice, right? So from the original statement, right? So it's indeed a more powerful generalization. Now let's also see that see the earlier statement that we wanted, some of the more intuitive statements that we wanted, if two vertices are there which is non-adjacent, then the number of vertex disjoint paths between them, internally vertex disjoint paths between them, the maximum number of internally vertex disjoint paths between these two vertices A and B will be equal to the minimum number of vertices that I have to remove from the graph, so that A and B gets separated. The minimum number of vertices other than A and B that I have to remove from the graph, so that the vertex A is separated from B in the remaining graph, disconnected from in the remaining graph, right? This two numbers are equal. So this kind of statements will follow from what we have proved. That we first look at how it follows from this already proved statement, right? So before the first statement I would look, because I want to look at this thing first, because the once you do this thing, the other proofs will be much easier. So here there is a concept called AB fan. What do you mean by AB fan? So here is a set B, and this is a graph G, and then here is a set B, and then we take a vertex A outside B. That means this A belongs to V minus B. Now we want to find some disjoint paths starting from A to B. Disjoint means disjoint paths except for this vertex A, means other than this vertex A they should be internally vertex disjoint, and that means here in vertex disjoint, that means nothing else should be shared. This should be reaching in different points, and then these should all be disjoint, right, except this vertex, right. They're starting here. This kind of a structure is called an AB fan. So we say AB fan, it looks like a fan probably. So the fan structure, right. So this is called an AB fan. The cardinality of the AB fan is how many such paths are there in from A to B. That is the cardinality of the maximum cardinality of an AB fan. So we will show that the essentially the maximum cardinality of the AB fan will be equal to, this is A, this is B. So this maximum cardinality of the AB fan will be equal to the minimum number of vertices outside A, other than A, that I have to remove from the graph, so that this gets separated from A. There is no more path from A to B, that numbers are same. So you can look at it once again, B subset of V and A element of V minus B. The minimum number of vertices not equal to A separating A from B in G is equal to the maximum number of paths forming an AB fan in G. So how do I prove this thing? So this proof is simple. So we will, this is our A, we rather consider the neighbors of A. This is called n of A, and let's define this as capital A, and so this is our P. So it's possible that some vertices here are A intersection B need not be phi, right. There is nothing like that. It's possible that there are some vertices, this neighbors may be in this B. Now it's easy to see that you consider the maximum number of paths starting from A and reaching B. This number essentially will be equal to the number of maximum number of AB, this capital AB disjoint paths, because if you consider this AB disjoint paths, they are not going to contain any none of this thing is going to contain A, because if you go to A you have to come back to this, right, because B was totally outside it, because the only way, once you go, the only way is to come back to its neighborhood. So because any AB disjoint path, AB path is going to contain a vertex of A once, so it will never contain any of these things. So what you can do is all these paths can be extended to A, and then you will get extended to A, and you will get an AB fan of the same cardinality. On the other hand, if you have an AB fan, you can discard A and its connections, and the remaining is going to be an AB, a collection of disjoint AB paths, right. You can immediately see that now it's already disjoint AB paths. So therefore this parameter, the number of disjoint AB paths, is essentially equal to the maximum cardinality of an AB fan here, once you take this capital A to be n of A, right. That is the only trick. Now also we know that this number of AB paths, disjoint AB paths, if the Menger's theorem is proved in this general setting, we know that it is equal to the cardinality of a minimum x that will separate this portion from this portion, right, A from B. So and then we just have to prove that this number essentially is equal to the number of vertices required to be removed outside A to separate this vertex A from this. You know that this cannot contain A, because if you contain A, right, even without A, this could have got separated from this portion. It's very easy to verify. So therefore, by the same kind of argument, we can say that the minimum vertices, number of vertices that separated this thing will also separate A from this small vertex A from B, and of course that set is without A in it, right? And of course the other way, right, if any collection of vertices that can separate A from this thing will necessarily have to separate this neighborhood from this, otherwise we still have a path. It's just a matter of carefully looking at it. It's very easy. So therefore this both the parameters are equal, and by Menger's theorem we have already proved that the number of disjoint A B paths is equal to the minimum cardinality of a separator between A and B. So that's it. So that will prove this thing. See, the key point is only to consider the neighborhood instead of that vertex itself, and then take it as A, capital A, and then B as the original. Now in a similar way we can show that suppose A and B are two disjoint vertices in the graph, then the number of internally vertex disjoint paths, maximum number of internally vertex disjoint paths between A and B is equal to the minimum cardinality of a set of vertices required to be removed so that A gets separated from B. For this thing also we do the same thing. We consider the neighborhood of A, this n of A, as the capital A, and the neighborhood of B as the set B. Okay, the neighborhood of A is the set A and the neighborhood of B is the set B. And now we consider these two parameters. The Menger's theorem would say that the number of disjoint this capital A to capital B paths will be equal to the minimum cardinality of a separator to separate A from B. We should prove that this number of disjoint AB paths, the maximum number of disjoint AB paths, is essentially equal to the number of internally disjoint vertex, so vertex disjoint paths between the small a and small b, the vertices. And similarly we have to prove that the number of vertices in the minimum separator for A and B will be equal to the number of vertices to be removed to separate A from B, right? So once you get these two things, then the proof is automatic. Well, I leave it to the reader to the student to verify that. So it's the same as the earlier one, while it is not very interesting to teach. Now finally, this would also allow us to make this statement. So again, so this statement, namely, so this was the last one we told, that A and B be two distinct vertices in G. Then if AB is not element of E, then the minimum number of vertices not equal to A comma B, I mean the minimum number of vertices other than A and B separating A from B in G is equal to the maximum number of internally vertex disjoint AB paths in G. Now a graph is K connected if and only if it contains K independent paths between any two vertices. So that's what K independent paths, K disjoint paths between any two vertices. How do I show this thing? So this is also, so you can see that suppose between any two vertices there are suppose there are K disjoint paths, then by definition we know that it's K connected, because you have to remove see, if it's adjacent, by removing some vertices you cannot disconnect them. If it is non-adjacent, so of course you can remove you have to remove at least one vertex from each path, then only we will be able to disconnect it. So it's K connected, right? So for any pair, if there are K internally vertex disjoint, or sorry, in disjoint AB paths, then it's K connected. Now is also see that suppose it's k connected, right? That means you have to remove k vertices to disconnect the graph. That means for every pair we want to show that, then in that case for every pair there will be at least k internally disjoint vertex paths. So how do you show that? So because see, for two vertices which are non-adjacent, definitely we have already shown that, because that is just previously we show that if it is adjacent, one path already is here. Now you can see that, right? So if there are no k internally disjoint paths between them, other than this thing, they will only be at most k minus 2 disjoint paths, right? In G minus this edge, if I remove this edge, only k minus 2 disjoint path will be there. So that will essentially tell me that. So it is k minus 2 plus, sorry, k minus 2 plus 1 is equal to k minus 1 connected, which is, so the, I mean, you can separate the graph G by removing just k minus 1 vertices. That will be a contradiction. How do I do that? So suppose, so this is the xy. So what I do is I remove this edge from this thing. Now you know, by assumption we have only k minus 1 disjoint paths between x and y. So one is gone now. So how many more are left? Only at most, yeah, like this. So at most k minus 2 paths are left. 2 paths are left. But if there are two k minus 2 vertex disjoint paths in between x and y, then we can remove a set of cardinality k minus 2 and separate x from y, right? Separate x from y. Now you can see that. So it's not true that, so there should be one more vertex which if you add this y also, see, one of this vertex can be added and you can disconnect the remaining graph, because this edge will go away with the this thing, and then we will get a k minus 1 separator. So this is why we will end up with a k minus 1 separator if there are no k k disjoint paths between any two vertices in this thing. So in other words, the k connectivity of a graph, namely the minimum number of vertices to separate graph, so disconnect a graph, is equal to the maximum number of right, sorry, overall pair. If you take any pair, right, you have to minimize over that overall pairs. So then you consider this maximum number of disjoint paths between those pairs. So that is what Menger's theorem says. So now we will go back to our proof. So this essentially all these consequences are more or less immediate, though when we are explaining it looks a little dull, and then they are not very difficult to prove. Even if you have missed some of the points here, you can easily figure it out yourself. So we will go to the more non-trivial part, namely the proof of this statement, that is this statement. So yeah, so let G equal to V comma E be a graph and A be subset of V, then the minimum number of vertices separating A from B in G is equal to the maximum number of disjoint AB paths in G. So to prove this thing, so we first observe that so suppose this k A B of G, the minimum number of vertices to be separated, has to be always greater than or equal to the maximum number of disjoint AB paths. Why? Because you have to remove at least one vertex from their disjoint paths, at least one vertex from each path, otherwise at least one of the path will remain as such. So how can we can how can we disconnect A from B without removing at least one vertex from each path? So this is true. The only thing we have to make sure is this will not happen, right? A B of G is strictly greater than this quantity is not possible is what we want to show. In other words, so the maximum number of disjoint, right, this is what we want to show. So suppose this is the cardinality of the minimum separator of A and B, then we want to show that there exists this many disjoint paths between A and B. That we will do in the next class. Thank you.